or sorry, Newton meters is equal to 0. So this will just give us our, what we had solved for last time. AX is negative 90 newtons. Right? Yeah, okay. So negative 90 newtons for that, and that will give us EX is equal to 90 newtons. But the difference in this problem starts when you're looking at the individual numbers. EC, since it has a moment within it, it's going to no longer be a two-force number, but that also makes AC a two-force number. So let's.
So that means you have too many unknowns to solve for the EC number.
Right. If let's draw EC here first. So we know EX, but we don't know EY. And then we have two forces here coming from C and a moment here. And these are no longer, because of this moment, we don't know what angle these are coming at. So all we can say is that CX is going to be equal to this force, and then CY is going to be equal to this force, but then we can't determine anything else about it. And if you're doing a moment equation, you're going to end up with both of these in there. I guess actually to get something here, if you take a moment from here, because you're canceling out those two forces, and then you have that moment. So I guess you probably could solve it like that. Let's do that, just to change it up. So we said EX is 90, and EY, there were 36 Newton meters, and then we'll just put these as CY and CX. So let's do some of the forces in EX is equal to 90 minus CX, which is equal to 0. So that will give us CX is equal to 90. Some of the forces in Y is EY minus CY is equal to 0. EY is equal to CY. But it's important to do a moment equation here to try to get force EY. So if we're doing the moments about C here, we're going to need these distances. So let's see. In this case, it was 240 millimeters, and then 480 millimeters. So some of the moments about C, we're going to have the negative 36 Newton meters from there, and then you have EY times of 480 newtons, and this is going to be negative. We've gone pointing into the board for a right-hand rule. So minus 4, and then since this moment was given in Newton meters, we need to multiply this by we need to turn it into a meter value here. So this one is now 480 over 1,000, and that's in meters times EY. And then, let's see. But now if we're doing our moments from this 90 newtons, it's going to be positive because your thumb's coming out from the right-hand rule. So plus there'll be 90 times the 240, and then this has to be changed into meters as well. So now all of these are in meters, so we can just go on with the problem. So now we can solve for EY here. Let's just plug this into a calculator. Oh, sorry, this is equal to 0. So that's how you're getting that. So we have 36 minus 90 times 0.24, and then dividing by 0.48, or negative 0.48. So this will give us EY is negative 30. Let me just check that that's right. Yeah, that appears right. Okay, so EY is just negative 30, and then from our original equation here, we had AY is the opposite of EY, so AY is going to be 30. So yeah, there are usually multiple ways of solving problems like this, because in this case there were only two members in the frame, but a lot of times there's going to be several members, and it's not always going to be as simple as to know which member you want to pick. So it's sort of like a puzzle. You need to figure out, based off of what information you already have, which member you can find more information about.
In class, he was talking about like if there's like 3 unknowns and 3 equations, and you can solve it, and then if there's 4 unknowns and 3 equations, it can't be solved.
Right. Yeah. So there's different ways of trying to figure out where to do it, but a lot of the times it's not always very simple to see where everything is known, especially when you're dealing with complex frames. So you sort of have to just try a lot of different problems and learn more about how to solve individual problems. So let's see, what time is it? It's only 1:36. Okay, well, it doesn't appear to be sharing. Okay. So that was all I had written so far. That went by pretty fast, so I guess I'll just look for another problem to go over. So here we go. We'll do problem 6.81. So next problem. This time it's going to be three numbers. Okay, so we have 3 numbers here, and this is actually a roller here. So this is a pretty basic frame. In this case, we're going to have a force here of 18 kilonewtons, and then we're given dimensions for different things here. So this is 3.6 meters between the pin and the roller. And then we have this distance is 2 meters, this distance is 2 meters, and the distance from here to the top is 2 meters. So that makes it pretty simple. And then we'll mark what all these points are. So we have A, B, C, D is where the force is acting, E, and then F is this roller pin. So it wants us to determine the components of all forces acting on number ABC. So I assume that just means they want us to find the reaction forces at A and F. So just start off a free body diagram of the entire structure here. And so we're going to have 2 reactions at A and 1 reaction at B, and then our 1 force acting at point B. So AX, AY, FY, and then we have 18. So some of the forces in the X will give us AX plus 18 is equal to 0. So that'll give us AX is equal to negative 18 kilonewtons. Some of the forces in the Y will give us AY plus FY is equal to 0. And then some of the moments. Okay, I see. They want us to figure out all the forces that are acting on member ABC. So
seems too easy.
yeah, this would be, if it were just looking for the reactions here, that would be too easy. So, so yeah, they want us to take into account the internal forces due to each of these members acting on AC. So let's see. We want some of the moments here. Let's see, do we want? We'll take that about point F, just because it's already in line with the 18 there. So we know that was 4 meters or 2 plus 2 there, and it's going to give us a negative moment there. So negative 4 times 18. And then we have AY here, which is also going to give us a negative moment. And then the AX is acting through the point we're taking the moment about, so we don't have to take that into account. So minus AY times, it was 3.6 meters, is equal to 0. So let's just plug that into a calculator. And it gives us negative 20. AY is negative 20. And then FY is going to be the opposite of that, so it's going to be 20. These are each measured in kilonewtons. So now that we have all of our reactions there, we can break it down into a few different parts here. So if we're looking at just number BE here, you see that it's connected to member ABC here. It's also connected to member CDF. But obviously it's connected at both ends, so we know it's going to be a 2-force member. So basically these forces here will cancel. So if this is BE, we know that forces are just going to be along the axis, and this force here we can just draw as coming inward. Actually, it's usually best to draw. Oops. Okay.
Why do the 2 forces in the Y direction cancel?
So this is another 2-force member one. So let me just draw this again. So again, it's going to be something like this. If we draw them, let's just draw them all acting in the same direction. So we'll say this is BX, BY, and the other one was EY, EX. So if we're doing some of the forces in X, just get BX plus EX is 0. Some of the forces in the Y will give us EY plus EY is equal to 0. And then when we do our moment equation, that's where it's going to cancel. So if we're taking a moment about B, we don't even need to know how long this length is. We'll just call it L for now. So some of the moments about B will just give us EY times L. It's negative because of a right-hand rule. And that's the only moment here, since both EX and EX are acting along the axis. So that's 0. It just tells us EY is equal to 0. And then from that, we know BY would also be equal to 0. So whenever you have a two-force number, you can just usually assume that it's going to act along the axis there. So it's going to act along the 2 points. So even if it's, like in that last problem, even if it's like this, where these are the 2 endpoints, you can just assume that it's going to act along this line that's connecting these 2 points. And that allows frames to be simplified a bit. So knowing that, let me just get out of the sheet here. When we're looking at number ABC, we know that at this point B here, we're just going to have one force going to the left, or going to the right there. And so we'd already solved for AY and AX. So let's just draw those in again. Obviously, these are both negative, so this one is negative 20 and negative 18. And then we have our 2 unknowns up here, CY and CX. So we'll just call this force BX. So now we can just do our static equilibrium about this. So some of the forces in the X is CX plus BX minus 18 is equal to 0. Some of the forces in the Y is equal to CY minus 20 is equal to 0. So that will just give us CY is equal to 20 kilonewtons. And now we need a moment equation. So it's pretty clear, since we have 2 unknowns at CY, we want to take it about point C. So let's look back at the original problem. We know this vertical distance here between C and B is 4. So that's going to be the moment arm there. And then the vertical distance to A was 6, and the horizontal distance is 3.6. So that'll just be useful for doing this moment equation. We know Bx is going to give us a positive moment. So we have our Bx times, we said that was 4. And we're going to have a positive moment to AX, but since AX is negative, it's going to give us a negative moment. So minus 18 times, this time it was 6. And then this moment here, let's see. So it's going to give us a negative moment, but since it's negative, we're basically subtracting that moment. So minus negative 20 times, and then the horizontal distance there was 3.6. So overall, this is going to give us a positive moment. And then that's going to be equal to 0. And so this will give us our Bx, which turns out to be 9 kilonewtons. Let me just check that on a calculator first. So let's see. 18 times 6 minus 20 times 3.6 divided by 4. Yeah, so that gives us 9. So now that we have that, we just need, what is it, CY? No, sorry, VY. We need CX. So CX is just going to be 18 minus. So it's going to be 9 as well. So there's our last.
Is there anything with distributed forces?
Oh yeah, I can do a distributed one. I don't know if I have one in the book here. Just look around first. No, I guess I'll just make up a problem. So. Okay, so in this problem, we have a triangular load, a cantilever beam with a 5 kilonewton force trying to hold that up. So now we want to determine the reactions over here. So we'll call this point A, call this point B, C, and E. So let's do okay, so first thing, like Professor Katz always says, the first thing you always want to do is find the resultant force due to that. So let's write this, we'll call this like W of X. Okay, so let's say X is measured, from here. So from that point, from point C there. So let's try and write an equation for W of X. So obviously it's going to be a linear equation. So we have mx plus b. We know at 0 is 0. So if that's our 0 point for x, we know that's going to be 0. So that just basically tells us that b is 0. And then we're just figuring out the slope there. So w of 5 is 10. So that gives us our slope is 2 kilonewtons per meter. So now we need to integrate from 0 to 5 of w of x dx to get our force. So that's just the integral. It's 2 times the integral of x dx. So that I just brought the slope outside. Yeah. So obviously it's just x squared over 2, so that'd be 5 squared over 2 is 12.5, but then you multiply by the 2. So this turns out to be 25 kilonewtons. And then you integral from 0 to 5 of x times w of x dx is going to be, again, 2 times integral from 0 to 5 of x squared dx is going to give us x cubed over 3 times 2. So let me just plug that into a calculator. I know Professor Castle usually just says for triangles, you take it 1/3 from the fat side or whatever. But it might just be simpler to do an integral equation here because that is telling you an exact measure from here rather than saying it's 1/3 from there. And you're going to need to do this anyway when you're dealing with distributed loads that aren't triangular. So it's good to remember this stuff. So it turns out this is, let's see, 83.3 repeating.
On the problem set, I was just lazy and just did like 1/2 base times height. Or 1/2 force.
Yeah.
1/2 base times the force.
Yeah. Yeah, I mean, obviously, that's an easy way of doing it, but, and actually, do you know if you're taking advanced? No, you probably take that in another couple of semesters, but advanced mechanics, you're dealing with how you basically have the same problem here, but you need, rather than saying it's statically determinate, you're saying that it's going to deform. And so there you have to do a lot of different things with distributed loads to get it to work. And I mean, it's a lot different than actually just doing an integral here. And it's not as hard as it might seem, but it's so good to know how to do certain problems like this. So this is actually giving the measure in kilonewton meters, and so then we divide by our force here to get our distance, so we just divide that by 25. That'll give us, we can call that, I don't know, x bar is equal to 3.3 repeating. So this is the force, and that's the distance from there that force is acting. So now that we have that, that's going to make doing the free body diagram a lot easier. So let's do the free body diagram here. So since we don't have any axial forces, we can just worry about the vertical forces here, or the shear forces. So this is 5 kilonewtons. We're also going to need a moment here. So we'll call this MA, FA, and then this is our FR, which we said was 25. And then we also need to say where this is acting. So that would be our 2 meters here plus our 3.3 repeating. This is going to be, what, 5.3 repeating meters away. So now, let's do our, I'm just going to try to move this stuff out of the way. Okay, so now I have a little more room to work. So some of the forces, like we just said, the forces in the X, there aren't any. We just didn't include it. Some of the forces in the Y, we have FA plus 5 minus our FR, so minus 25 is equal to 0. So that will give us our FA is 20 kilonewtons. We need a moment equation, so some of the moments about point A would give us MA times, I guess, actually, I think I drew MA backwards. So let's just draw MA as being the other way around. I just want it going clockwise so that it's positive. But I guess it really doesn't matter. So then we have our 5 kilonewtons times 1 meter. And that's going to give us a positive moment as well. So that's plus 5 kilonewtons times 1 meter. And then we have our FR is going to be our negative moment there. So it's going to be minus 25 times 5.3 repeating. And this is 0. So now we have our MA is going to be 25 times 5.3 repeating minus 5. It's going to be 128.3 repeating, and that's going to be in kilonewton meters. So it's a pretty simple problem there, just showing how you would get a distributed load. So it looks like we're just about out of time. And there will be one more before the test on Monday, and then the test. You know, it seems kind of silly to have